Alright, welcome to the second half. Let us continue with our final review. Let's move on to the newer stuff. Okay, newer stuff that I will review for you. So this is just a greatest hits thing. Do take a look at the book, all of your assignments, all of your Zybook stuff, and ask me any questions about anything. So let's start with searching. So the idea is we want to find something. We take so much care to make all these different kinds of cool looking data structures, or we put stuff in memory in a certain way to hopefully get it back out again later, hopefully quickly as well. And so usually this is storing something that you want to get back at a later time, right? I'm searching for something. Okay, maybe I'm searching for the 0 or something like that, or something that doesn't exist. Maybe I'm searching for 1 in this array. Okay, and it doesn't have to be an array that you're searching through. In CSCI 41, if you take that, there's plenty more data structures than that. Maybe it's a linked list. You know about those now. So we just have something. We have some data structure, and we're looking for something else. Okay, we talked about it in terms of vectors / arrays, so maybe I'm searching for 0. If the vector is, or the array is unordered, we have no clue which comes first, second, third, like there's no relationship, then we just have to, we're forced to scan the entire array from left to right, or right to left, whatever you prefer. As long as you visit every element, you, in the worst case, have to look at everybody to determine, oh yeah, it was there in the last spot, or it wasn't there at all. See that? So yeah, linear search is just like that. You go through the entire array, left to right, and you return back of the index of the value that you were searching for. So maybe if it was 0, you'll give back the 0, 1, 2, 3, 4, 5. You'll give back 5, because that's the index in the array where you found your 0. Okay? And if it didn't exist, if you were searching for 1, you get like here, and it's still not 1, you give back -1 otherwise. That's just the standard way of doing it. And linear search doesn't matter the array, it will always work because you have to look at every single value. If it's there, it'll find it. Okay, that's pretty intuitive. Doesn't matter the shape that the vector or the array is in. Binary search, on the other hand, can save you a whole lot of time if you know that your array was ordered. So let's pretend, let's sort this 0, 3, 5, 6, 7, 8, 9. If I know that my array is sorted, then I know I can play the guess the number game. I can be like, okay, the best thing for me to check first is the middle. And if the number that I'm looking for is smaller than that, I can cut off the rest of this entire array. So you repeatedly search in the middle of your search space and have each time what you're looking through. Okay? That's binary search in a nutshell. Exploits the order of the elements in a sorted array. Sorted is key. Key. And the reason for that is because if I'm looking for like 4, then you know that looking in the middle and seeing 6, every index that is greater than this one, then the middle index must be bigger than 6. So it's certainly not going to have your 4 there. Okay? But everybody less than you could contain you. So let's look on that side. Okay? And the game that you play to get the maximum payoff is always start in the middle of your search space. And your search space is initially the whole darn array. Okay? And then you'll cut it off to one side, left and right, as you go further. Okay? And you can only cut off the size of the array so many times before you get down to a single element, or you ran out of things to check. Okay? So let's do binary search. I'm going to implement that for you, and then I'm going to show you how it's working with this vector, 2, 4, 6, 8, looking for the number 2. So let's use arrays, because why not? Int arr 2, 4, 6, 8, 10. And its size is 5. Let's remember that. And now we have binary search. So it's going to return the index, remember? Binary search. It takes the array, int arr You could also pass it like a pointer, it doesn't matter, because arrays are pointers. Let's just do that. And then you have the indices that make up your search space. You have your low index, you have your high index, and that's all you need. Of course, you still need to pass along, though, the thing that you're looking for, val to search for. Okay, it's an array of ints. You better pass along an int. And this is all you need. So you can say cout, let's binary search this array, starting with the initial search space of the lowest index to check is 0, the highest index is 4, because that's size -1, and then let's look for 2. Okay, and so we should find it. We should find it at index 0, but it's going to take a while to get there. And we can also search for something that doesn't exist, like 5. The number 5, it's not in there, and so this should output -1. This should output 0. Yeah, that's the game. So, we're going to keep all this in our minds. We're going to take a look at the middle as often as we can. So, here's what you do. Let's see here. What's the best way to do it? Yeah, so the idea is it's always a loop while low is less than or equal to high. If those ever pass each other, low is always supposed to be less than or equal to high. If they ever pass each other, your search space is empty. That's the key. Okay, so find the mid. That's the first step. And see which side your value is on. And search in that direction, okay? So if you got really lucky, you might have found the value at the middle. Okay? So the mid index, that is low plus high divided by 2. Integer division, that's fine. It's not a big deal. Somewhere in the middle, one of the two, if it's even, int mid. That's the index of the mid. And then we want to figure out, was that anything close to what we were looking for? So I think here's what we can do. We'll say if the array at this mid index, was that bigger than what I'm searching for? Is the value that I'm looking to find, is that smaller? Okay, same question. So if it is, everything to the right is too big. Mid was too big. We should search to the left. See that? So our new low index stays the same, but high becomes mid -1. That's the idea. Because it wasn't in mid, so the last potential index where it could be, because it's smaller, is mid -1. Okay? And then we do the opposite. If the value that we're looking for was bigger than the midpoint, the thing in the middle, then mid was too small. We got to search to the right. Okay, and so that means change low. Low equals mid +1. Because the first index where it could be, if mid was too small, is mid +1. That's the next one that we haven't looked at yet. Okay? Otherwise, we found it. It was right here at mid. So let's return mid. That was the not the address, that was the index of the val to search for. That's quite nice. And so this will eventually return if we ever find it. Otherwise, low will pass high, and that will stop the loop. If we ever get here, high is less than low, which means our search space is empty. The impossible happened. So return -1, indicating that we didn't find the thing. Okay, so that is binary search in a nutshell. Let's see if it is happy. Yay. So we have 0 and -1, and it found the thing. That's great. Okay, so that's binary search. Let's make sure that I haven't gotten to anything here yet. No, good. In the cheat sheet. We'll get there. Don't you worry, we will get there. So let's see. Yeah, so let me show you how it finds this 2. This was our array. Let's make it large. And I know I'm going to need this later, so we're going to do this. Initially, low is here, high is this index, right? Because it's 0, 1, 2, 3, 4. And we're looking for, like the val to search for was 2. Okay? So we're going to compute the mid. Mid ends up being the low plus high divided by 2. So that's 0 plus 4 divided by 2. That's just 2. So this is mid. And so that's what we check. We check mid with val. And we notice that it's too big. So our bounds are going to be this. We're going to swap, well, mid will change in a second, but we need to look through only this side of the array. Okay, we want to cut off this part. So I'll just draw a line through all the places we don't care about anymore, because we know that it must be to the left here. Okay, so low becomes, it stays 0, and high becomes mid minus 1, which is 2, or sorry, which is 1. 2 minus 1 is 1. So now, low is here, high is here, and we're still looking for the same value. Okay, so then we take the average. What is the mid index? 0 plus 1 over 2 integer division. That happens to be this one. And oh man, do we hit that else case? We found it. We'll return back the index 0. If we didn't find it, if we were searching for maybe 1 or something, we would notice that, oh, this is too big. I need to change my high index, right? High needs to be mid minus 1, but mid was 0, so high comes to be -1 now, and that's what happens when it doesn't find it. Okay, that means that the search space was empty because some impossible thing happened. High is always supposed to be a bigger index, but we just try to make it smaller. Okay, that's the idea. So that's binary search, and now it's time for recursion. Are you ready? So recursion is all about finding a problem inside of itself. So let's take a look at the beautiful cheat sheet that I've made for you. So for example, for factorial, you are going to always, when you do recursion, this is like your thought process. You're going to write out your nice example for some number. I like 5 for no good reason. And then you're going to think long and hard about the answer and try and find a smaller version of the problem inside of itself. Okay, that takes some thought. That's the next step. Find that problem inside of itself. And then you get to assume that the recursive call always works, which is the call to the smaller subproblem. Assuming P4 gives you the right thing, create the recursive case by generalizing this example. Okay, so the recursive call needs to use a smaller argument, and so you notice that, oh, generically, P of n for any n is just n times P of n minus 1, which is n factorial equals n times n minus 1 factorial. Yeah, and then you'll keep on writing out what needs to happen, P of 4 calls P of 3, calls P of 2, calls P of 1. When do you stop? That's your base case. Okay, you'll notice that, okay, a good stopping condition is P of 1. 1 factorial will just say that's 1, call it a day. Okay, no more recursion necessary. And then you keep on going back to step 1, making sure that everything is working, and eventually you program it up. Okay, so that is the idea of recursion. And yeah, so let us have some examples of recursion. Let's do x to the power of n, and then I'll do a recursive binary search for you. Okay, so let's see here. Oh shoot, one thing that I did here, binary search, val, low, high, I didn't have to give these as parameters. I could have just given size here as the parameter, and I could have calculated the first low and high based on that. That's just an aside. We're going to need them to be parameters to do it recursively though. Okay, so x to the power of n, that's just, let's pretend we're doing x to the 5. That's just x times x times x times x times x. Oh man, there's x to the 4. So generalize x to the n equals x times x to the n minus 1. Ooh, that's a recursive case. What's the base case? I think x to the 0 is a good one to stop at. That's defined to be 1. Yeah? So that can be our recursive solution. So, recursion.cpp. I don't know, let's do, this is just x to the n, right? It's power. Let's do, I don't know, 4 to the power of 3. Well, let's do a nice power 2. This is computer science after all. 2 to the power of 5. So here's how we can do it. Int pow. Technically it could be a double. Double pow. The first number can be a double. The thing that you're taking to a power. Double x. And then int n. This has to be an integer always. Okay, so base case, recursive case. If n is 0, you're trying to take x to the 0th power. Return 1. Otherwise, return the power x to the n minus 1 times times n, and I'll do that on the left. Okay, that's all. 2 to the 5 is 2, 4, 8, 16, 32. Let's confirm. And I encourage you to draw these trees to understand why it's working. If not, come to office hours and ask me to draw the tree for you. Okay, draw the stack diagram. And that will make it make sense. And let's see, x, n equals 0, return 1, pow, 2 to the 5. Why is it saying 120? That is a bit off. X to the n minus 1. Oh, you know what happened? I think we're calling the standard library pow, potentially. So let's do power, just to be safe. Dun, dun, dun. I think that'll help. Oh no, it's still 120. Okay, in that case, something is a bit off. 2, 4, 8, 16. It's supposed to be 32, that's for sure. Oh, sorry, it's supposed to be x. X times pow, 2 to the 5. X to the n minus 1. See? Excuse me. And now we can go back to as it was. There we go. 32. I'm happy now. See? So always remember to get your recursive case right. Otherwise, it doesn't work. Okay, recursive binary search now. This one's going to be fun. So you can make low and high your parameters, and you can just change how you pass along low and high. Okay, you just return the result of the recursive call. It's going to be weird. And let me walk you through how I think about this. Okay, so let's copy over the previous one, this binary search. Whee. And we'll call it again. Cool. And we give it the starting low and high. That's necessary. And then the rest changes. There's no more loop. No more loop at all. The recursion is the loop. Okay? This is weird. I know. So, we have two base cases. I think we can get away with just one. The base case is the search space is empty. That's when we can immediately return -1, right? Otherwise we have to look in the array, maybe do some looping. This one, we know the answer. If low is greater than high, return -1. We're done. Okay? Otherwise we can still continue on to the rest. Otherwise, we find the mid. Okay? Find the mid and see which side of the array it's on, and we want to change our search space. And now, we don't reset high. We don't reset low. If we found it, we return the answer. That still stays the same. The way that recursion has the loop now is mid was too big, we need to search to the left. Well, I'm going to assume that my recursive call to binary search to the smaller search space is going to work. We get to assume, as long as we build up the answer correctly, that the smaller recursive call, and it's smaller when the search space is smaller, is correct. Okay? So, okay, I need to look to the left. Well, I'm going to throw that off to the smaller recursive call, which I get to assume is correct. ARR, I'm going to, if I'm looking to the left, low stays the same, high becomes mid minus 1. Oh man, that's a new high parameter now. Same value we're looking for. See that? And if mid was too small, that means low needs to change. We need to look to the right side of the array, which means low needs to be mid plus 1, and high can stay the same. Isn't that cool? There is no loop anymore. The loop is recursion. This is a smaller recursive call. We get to assume it does the right thing. Smaller recursive call. We assume it does the right thing. It finds the answer if it's there, or it doesn't find the thing if it's not there. Isn't that cool? So that is recursive binary search in a nutshell, and it works. Okay? Feel free to ask me about this. It's a weird little topic, but it's fun. Okay, so next, let's move on to makefiles now, and this is also here in the cheat sheet. So makefiles are all about, we have multiple files and we want to compile them in a nice easy way. We want to know, like, we just want to say make and have it recompile what needs to be recompiled. If we didn't change a certain file, don't recompile it because that was unnecessary. We'll go through those intermediate object files, those .o files, and that's how we will make our final program. Okay, so this is all the stuff that needs to be in a makefile. This is how you can run it and how it all works. So please look at all this, but I'll give you the overview now here. So remember, it all comes back to, I swear this is a word, it all comes down to how does compilation really happen, okay? Compiling is, as far as G++ is concerned, that is taking one single file, a single file, and turning it into machine code. This is not GCC, G++-C. That's the compilation process, okay? Unfortunately, they're both packaged together in G++, but we want to think of it as two separate ideas. The compiler makes object code for a single program, okay? And if you ever want to make a final executable program, you have to bring in like cin from IOStream. You need to bring in the vector library, which has all been pre-compiled for us. And so it's all linked together. Your code, other programs that you've also wrote, library functions, those all are brought together by this linker, okay? And then that finally gives you your program that you can then go and run. If you don't give a name, it's called a.out, right? So that is the difference, compilation versus linking, okay? And for makefiles, we take advantage of separate compilation. So each file goes to a .o file. It gets compiled just by itself, okay? And because of that, we only have to recompile what we changed and then just link that stuff together. Linking is fast, compilation is slow. That's the idea. Okay, so a makefile has to be called makefile. There are some other ways to name it, but we're going to go with makefile in this class with a capital M. And we have our targets, we have our requirements, and then we have the rule body, which tells us how to make our target using our requirements. So let's just compile our library. Let's make our recursion program as a library. Okay, so let's bring in, I don't know, let's do this. Let's make a recursion folder. Darn. Let's remove the compiled file, make a folder called recursion, move recursion.cvp into the recursion folder, and then let's go into the recursion folder, and we're going to break this up. We're going to make recursion.cvp, we're going to make main.cvp, we're going to make recursion.h. How about that? So I have these three files. Let us start in recursion.cpp. Okay, so main.cvp is going to hold the main function. So let's take that out of here and bring it down to there. delete, paste, and then all this stuff can also go up in the main.cvp file. So now it should be happy, but it doesn't know about power binary search. And this is where this library comes into play. Here is the recursion.cvp file. It's going to make a use also of recursion.h. It's always customary to include your header file, even though it's not necessary for this one. And then the header file is where you declare stuff. We're saying, okay, this is the declaration of, this is the declaration of the PAL function. Here's where it's going to live, okay? This is the declaration of the binary search function. This is all you need to know in order to call it. Okay? And remember your header file guards, just to make sure that there's no infinite inclusion. That's very useful. And so yeah, this is all that main needs to see when it gets compiled by itself. Now it's happy. So the goal of a make file is to compile just main.cvp by itself, and then just recursion.cvp by itself, and then link them together. Okay, so we'll go through those .o files to get there. The name of the file is called makefile, and now we're writing in the makefile language. It's not C++ anymore. So we want to make main.o. We need main.cvp. That's a requirement, so it goes after the colon. And then in order to make main.o from main.cvp, we say g++ standard equals C++17-c main.cvp. It'll get created into main.o. It will get compiled into main.o just from that. Okay, so that makes main.o. Then we want recursion.o. That requires recursion.cvp, and we're going to compile recursion.cvp into its .o file. And then finally, usually the main course goes at the top so that you can just say make by itself. We want to make a file, an executable file this time, called main, and it requires both of our .o files. If they don't already exist, we got to go make those. Or if one changed, we got to remake it. Those are our requirements, and then using those requirements, we just link together those two files into a file called main. Yeah? And that is the idea. So now I can just say make by itself, because it'll run the first rule, or if I want to be specific, I could say, have to be in this folder though, I could say make main. Okay? And so what it will do is, oh shoot, did I not delete it from here? Oh, I didn't save one. I didn't save this. You're saved, you're saved, you're saved. Okay, I think we're good. So back in the make file. Let's delete everything. Okay, make main again. So it'll make the two .o files, because it didn't have them. Because it goes to this rule, it sees, okay, what do I have? Does anything need to be remade? And it notices that it doesn't even have main.o or recursion.o, so it goes and makes them both by following these rules. And then now it's ready to finally do this last one. And it tells you what it's doing in order. That one first, then that one, then this one. And now I have three files. These two intermediate compiled forms and this executable file called main. Yay, and it works just the same. That's the beauty of it all. And the whole point of make files is, of course, to save compilation time by not recompiling too many things. But the nice thing is that it also just notices what needs to be recompiled. If I add a line here to main.cvp, watch what happens. Let's search for 10. Say make main again. Notice that it doesn't recompile recursion.o. It just noticed that this one changed. Recursion.o is fine. We can link together with its old version. It didn't change. But we need the new main.o. See that? That's the key. That is make files in a nutshell. Okay. So that is, that's all I wanted to say there. Ask me if you have any questions. And now we have two more slides. So the first is bitwise operations, and that one is not too bad, I hope. It's just, you're doing stuff. You're performing logical operations. You're just like treating every bit of a number as true or false. If it's a 0, it's false. If it's a 1, it's true. And you're performing these logical operations like AND on each digit in a certain place. And you're replacing that place. Okay? AND is a binary operation. OR is a binary operation. XOR is a binary operation. NOT is a unary operation. So it just takes this number and inverts every single bit. Left shift takes a number to shift to the left by. Okay? And it adds some zeros, potentially knocking off some bits on the left if there were too many. Okay? That's the idea. So remember that every int that you have has a bunch of 1s and 0s between index, like it has bit 0, bit 1, bit 2, all the way to bit 30. Yeah, this is 30 and bit 31. There are 32 bits total in an int in C++. Okay? Doubles have 64. Chars are a byte, so they're 8 bits. So just keep all that in mind. Usually we work with ints in this class. But yeah, bitwise operations perform those logical operations on the bits of numbers. So yeah, you got all of these nice ones. Remember that AND is good for checking bits, because you can just like take some number, and if I care about this bit right here, see if it's set or not, I can just AND with a 1 only in that spot. And if it's a non-zero number at the end of the day, then I knew it was there. OR is good for setting bits, because you can just OR by something, and then it'll automatically be a 1 in that location. And XOR is good for flipping bits. Okay? So, because if you do 1 XOR 0, or you XOR by 1. So like if you do 0 XOR 1, it becomes 1. You set it. You flipped it. If you do 1 XOR 1, you flip it. So it becomes a 0 now. That's the idea. Okay? So let's make two functions. Let's make multiply by 2 to the n and flip bit. Okay. So I'll take both of these, and we'll do bitwise stuff. Let's go back out into the main folder, and let's work there again. Okay, so do I still have these? Yes, cool. So this will be multiply x by 2 to the n. It'll return a new int back. Flip bit, I guess it might as well also return a new number back with the flipped bit. So here's the idea. Here's what we want. This first one, multiply by 2 to the n, returns x times 2 to the n. Okay? That's what we want. And then flip bit returns x with the bit numbered which bit flipped. If it was a 0 in that bit, it becomes a 1. If it was a 1 in that bit, it becomes a 0. Okay? That's the goal. And so let's do this one first. Multiply by 2 to the n. And this one's not too bad, because if I want to take this binary number, like if it was 5 times 2 to the, I don't know, 2 to the 2. So it's 5 times 4, that's 20, right? What's 20 in binary? Well, I can promise you that it was, if that's the 5, I can promise you that the answer is 10100. Well, let's confirm that. This is the 1s, 2s, 4s place, 8s, 16. So it's 16 plus 4. Yes, that is 20. So when you want to multiply by 2 to the n, any number, you just shift it. You just shift it left. You add some zeros on the right. That's all. Okay? So this one's easy once you think about it. Return x, shift it left by n. Isn't that nice? So cout, multiply by 2 to the n, 5, 2, and L. Do I have any G++s? There's one. And it's 20. Very nice. Now Flipbit is going to be a bit fancier. So the idea with Flipbit is if I have this number, like, I don't know, 1011, and I want to flip the second bit, 0, 1, 2, 3, this bit right here, I want to flip it. I want to XOR with the following. I want to make sure that all of these other numbers stay the same. So I'm going to XOR those with 0. Because if there are a, let's see here. If they are a 0, they will stay a 0. And if they are a 1, they will stay a 1. Okay? And then this one, the one that I want to flip, I put a 1 there. I XOR with a 1 in that location only. And that will make sure that I flip that bit. It'll become a 1 now, if it wasn't already, but if it was a 1 before, it'll become a 0. Okay? That's the idea. So we just, we XOR with a number 0 with only one bit set. Okay? With a number with just that bit set. Okay? XOR X with 1 shifted left by which bit, because that will make a number with only one bit set, that one that we cared about. Okay? That's the idea. So if X was whatever this was, and which bit was 2, it would XOR it with this number. Okay? Because 1 shift left 2 is 1, 0, 0 in binary. Okay? That's the beauty of it all. So, not sure what it is, but let's confirm. Let's be like, okay, this one was 3, 7, 15. Let's do 15 and then it's 2. Flip the second bit. And it should give back 1, 0, 1, 1, which is, I guess, 15 minus 4, right? So that is 11. Hey. Okay, so yeah, it's just noticing all the tricks that have to do with binary numbers. Okay, so that is flipping a bit and multiplying by 2 to the n. Hopefully that jogs your memory of what bitwise stuff is. Those are bitwise operations. Not too bad, I hope. And then the last thing that we have to talk about today is exceptions. Okay, so let's go there on the slides. Exceptions are just a way to tell somebody, tell the user of your library that you're writing, maybe, that something wrong happened. Like you did something wrong and I can't fix the problem. You have to fix the problem. Okay? Throwing an exception is giving the problem to somebody else. That's the idea. It can transcend function calls. It can jump out until it finds a catch block. That's the idea. It's always try catch. Try catch, try catch. Okay? So you try to do something, and then you catch an exception if you find one. Okay? That's the idea. So let's do this. Let's do these examples, which luckily use some of the code that we've already written. Okay? So do read up on all of this. It's you throw the exception, and it should hopefully be catched by a catch block somewhere. Okay? And we usually catch things by reference. Okay. So the first example is we're going to take our recursive power function and throw an exception when we get a negative argument. Because otherwise that would cause an infinite loop otherwise, right? So let's do that. Let us copy in our recursion implementation here. There we go. And then might as well get the other one too, the Flipbit ready to go. Here is that. So all of these are nice, but some of them don't work, right? I could say pow, I don't know, double, let's say 2 to the power of -2, and this will never finish, right? This should never work, because it'll always get smaller and smaller and smaller and never actually hit the base case, which is n equals 0, right? That's a huge problem. Oops. There we go. Segfault. I just kept trying to call the function a million times and I ran out of memory. Okay, so let's fix this by throwing an exception whenever we get a negative argument. And we can use one of our standard exceptions. We like to use runtime errors, right? That's defined in standard except, so we'll include that. And then we can say this: if n is less than 0, throw a runtime error. Can't handle negative powers, exponents. Okay, and this will stop the program. Here, it'll stop the pow function. It'll be like, okay, something went wrong. Let's give back that wrongness. Let's throw this exception in and pray that somebody catches it and fixes the problem, because I can't do my job if you give me a negative number. It's your problem now. Fix the way you called my function. Okay, that's the idea. And so we threw the exception and it stopped the program because we didn't catch it. Okay, that's what exceptions do. If, though, we caught it, then the program would be able to continue. Runtime error E, we can print our exception. E.what is where that string is stored. And then hopefully we can recover in this catch block and try it all over again. Okay? That is the hope. Fix the error, try it again. Okay, so our program ends normally this time. It would have done any more code down here because we caught the error and we supposedly handled it. Okay, that's the whole point. Throwing an exception hands off the error handling to somebody else when you cannot recover yourself. Okay, that's the goal. So that's the first one. And the next one, let's throw an exception if we try to flip an invalid bit. So if we're trying to flip bits of an integer, there are only bits 0 through 31, right? You can't give a number less than 0 and a number greater than 31. So let's encode that. Let's make our flip bit a bit more resilient. Pun intended. So if which bit is less than 0 or which bit is greater than 31, those were invalid bits. Throw a runtime error. We have a problem. You tried to flip the wrong kind of bit. And you don't have to throw just runtime errors. You can throw any type in C++. You can just be like, throw 42 and just hope that the user understands that this is like some kind of error code or something. That's totally possible. Not a problem. Try. So this will go wrong if we try to do this. Flip bit 42 of, let's try and flip the bit 100, which doesn't exist in a 32-bit integer. And so we'll catch the int. And hopefully use that to determine, oh yeah, this was error code 42. We tried to flip the wrong bit. So let's recover and try again. Yay. So it caught the 42 there. And that is exceptions in a nutshell. Okay. So that's everything that I had to review. Please look over all the stuff, all the resources, including this handy dandy cheat sheet, and yeah, use it all to your advantage. Please come to office hours if you have any questions about anything at all. But that is older stuff and newer stuff, and that brings us to the very end of this class. So you made it through. Pat yourself on the back. You did it. Yeah, yell at me if you have any questions at all. But otherwise, I will see you during the final. So good luck.